Hey, good morning, Chem 20s. I want to talk today about titration and how to do titration STOICH. So a couple of definitions from your textbook, and I have a few videos up to help you guys through this material. What is a titration? What is the titrant, the sample? Well, a titration is basically a process that chemists use to find the concentration of an unknown solution. So they have one solution, they know its concentration, but the other one they're trying to find. And so they take a sample, and that is the one that typically they know it's got a volume, and they put it in Erlenmeyer, and then they're going to titrate it with a solution, the titrant that's in the burette. So two important words for you guys to know and to memorize is the equivalence point versus the endpoint. These are different things. Theoretical means you can't see it, right? We're talking about moles. So we're talking about the moles of the titrant. Maybe the acid is equal to the moles of the sample, the base. At that exact point in time, we have completely reacted the acid and the base, and they're equal to one another. You can't see that though, right? That's a mole. A mole is something that's a theoretical value. What you can see though, the empirical, the observable thing, is the endpoint. And that's why we use an indicator. You can see its color change. Like it goes from colorless and all of a sudden it's pink, right? And so that's an example of using phenolphthalein. It undergoes this color change. You know that you've reached the endpoint of the reaction. And it's a measure of what's happening inside of the solution where the moles of acid is equal to the moles of the base. That it's a measure of. Now that's our theoretical. So when you do a titration, you're never going to do just one trial, right? Typically you do about 3 of them, and you're going to average them together. And all 3 of the trials have to be kind of close to one another, typically within 0.2 mils. And I'm going to show you guys an example of that in just a second. Okay, so some of the equipment you're going to be using, the burette is where you put the titrant. And so you are going to use a funnel and you pour the stuff in here. You get an initial burette reading, and you've got your sample, usually a known volume, usually around 10 mils or something like that. And so this is in the receiving flask, the Erlenmeyer flask, and you can control how many drops are coming out by this little valve here called a stopcock. So you've got your initial, how much you're starting with, and then over time you're releasing little drops of this titrant, and it reacts with the sample. And then at the end, once we see our end point, we see this color change, we know our reaction is done. And then we can take and find the actual volume that was used. And the volume of the titrant is going to be the final minus the initial. So using that information, we're typically given in a titration, a sample problem. We're asked to find the concentration of one substance. So here's a commercial solution, and we want to know what is the concentration of it. So we're starting with one thing. We have the mass and we know the volume, but we're not using that entire volume. Like we're going to make up a great big solution like 100 mils, and from that we're only going to take 10 mils of it at a time for each trial. And so this is what I know, right? I know my sodium carbonate, and I'm trying to find this HCl. So when I get a table of data like this, I want to fill out everything in the table. So I've got my final minus my initial is going to give me how much volume I use. In this case, it's HCl per trial. So I'm doing that again for trial 2 and 3 and 4. And which one doesn't belong? This guy, right? Trial 1 is way off. Also, looking at the indicator, they're telling me up here that they're using methyl orange as the indicator. And if you go and look on your data booklet, you'll see that methyl orange is red at a pH of less than 3.2, and it is yellow greater than 4.4. So that in-between range is the range we're looking at. When you select an indicator, you're always looking for the dash, right? Like 3.2 to 4.4. 4 would be orange. That's the in-between value there. So you can see this guy doesn't belong either, right? He is the too acidic end of the spectrum. So obviously you added too much here. We say that you overshot your endpoint. So that guy is a no-go. We're going to trash that trial, but we want to use these 3 trials here. They're all within 0.2 of one another. And so we are going to use them to do our calculations. So I'm not using this first trial. We overshot the endpoint. So we're going to average out these next 3. What's the name of the indicator? Well, I just said that's methyl orange. And so he's going to be red at the acid end, less than or equal to 3.2. He's going to be orange in between the range here, between 3.2 and 4.4, and anything above 4.4 in the base end of the spectrum, he's going to be yellow. So you just read through the equipment. Okay, we're obviously needing safety equipment. We're taking the mass and making a sample of our sodium carbonate, and then all of the titration equipment that we need. Okay, so how do I know what's going on here? What is going in the burette and what is going into our BR sample going into the burette? Well, this is how I read it, and it's a titration of something with something. So if it's of Na2CO3, this guy is our sample, and he's going in our flask, and we know his volume, right? That is the known. So we know this guy. We made up a big 100 ml batch of it. So I've got 100 mils, but I'm not going to take all that 100 mils in one go. I'm only going to put 10 mils at a time into my sample, and I'm going to use something called a pipette to do that. So here's my 10 mils of my known. I know this guy's concentration. Why? Because I've got a mass and the volume, so I'm going to show you how to calculate that in a minute. It's this guy titrated with this. So this guy is going in the burette. This is the HCl. This is my unknown. I don't know what his concentration is. That's what I'm trying to find. I just figured out what his volume was by doing my 4 trials, but this is who I'm trying to find the concentration of. Okay, so a couple of questions here. It says, why should you swirl the sample solution? Well, you're mixing it. And 1 drop is actually, you get up to a certain volume, and then 1 drop is going to change the indicator to its endpoint. Putting a white piece of paper underneath it helps you see the color change more easily. If you add too much, like we did in that first trial, you got to get rid of it, right? You got to redo, and you can't count that one. So you overshot it. You're going to do another trial. And then how do I determine the volume of HCl? Well, I'm not using that first trial. I'm only using the last 3. Now, 12.7, 12.8, and now this would be my answer here, but actually what my calculator shows me is 12.7666 repeat mils. So if I'm asking you to determine the volume, this is an answer, and so you're rounding it, right? But on your calculator, you're actually going to keep all of these digits going forward because we're not done our calculation yet. Okay, so keep all these digits on your calculator for doing our calculation. Okay, and then you set up your balanced equation. So Na2CO3 plus 2HCl. And the question is asking us now, calculate the concentration of the hydrochloric acid. So the main big step now is to write down what do we know and what do we want. And so we got to go back to this data chart that we had on the previous page. I just pasted it here so we can have a look at it. Okay, so we've got a whole bunch of information, and I know I just jumped right into that, but that's okay. I'm going to walk you through what we're doing here now. So we are starting with this mass of the sodium carbonate, this base. So we know his mass. We look up on our data booklet, sodium times 2, 1 carbon, 3 oxygen. We find the molar mass. And we're making 100 mils of solution. So again, we're making a big batch of solution, 100.0 mils. We're not using all of that. We're only using 10 mils at a time. So each and every time we're going to pipette 10 mils into the flask. And now we have 10 mils, and this is what we call our sample. In the meantime, we know that we've averaged out our number of mils, and we can convert that to liters. That's our volume of the acid. It's this guy who is our unknown. So he's going in the burette. He is the titrant. We're trying to find his concentration. And now, guys, everything else should look familiar. Everything else from now on out is just STOICH, and you've already done lots of STOICH. So here's our 100 mils that we're making up. How are we making this up? Well, here's how we made up our solution. We took this mass, we weighed it out, we divided by the molar mass. This is our base, this is our known. This is our sample that goes into the Erlenmeyer. And so our original concentration, and we're going to keep all these digits on our calculator, is 0.1500 blah, blah, blah moles per liter. And so that goes in our second bracket, right? We always start with our volume times by our concentration. Moles per liter is always used as a conversion factor. So here's our step 1 up here is done. We wrote down all of our values. Step 2 is finding our moles. That's these first brackets. Then step 3 is our mole ratio. Well, we get that from our balanced equation. There is 2 moles of HCl for every 1 mole of our sodium carbonate. So again, we made up 100 mils of this solution. We use a pipette and we suck out only 10 mils per trial, and we put that into our Erlenmeyer, and ta-da, there is our sample. Okay, so the STOICH now should look familiar, right? This stoichiometry, you're finding our moles of our given substance. We've got our mole ratio here, and then we divide by this volume. We've kept all of our digits on our calculator. So liters times concentration times mole ratio divided by liters. And what do we end up with? We end up with moles per liter. But there's one more thing that we have to do before we finish. Well, we got to pay attention here. It said we diluted the original solution by a factor of 10. So what do? We now times this value that we just found on our calculator by 10. And this is now our final answer. We'll check our digits: 3 sig digs, 3 sig digs, 4 sig digs, 4 sig digs. So 3 sig digs is the lowest in my final answer. And now I solved for my unknown. I now know what the concentration of HCl was. Okay, so now, guys, just do some practice problems. You gotta do some more STOICH, right? You gotta do some practice. There's one more question in this booklet and some practice problems. And as always, I'm an email away. So if you need help, you have questions, michelle.ledeen@ghsd75.ca. Talk later.